We're going to continue on in our lessons of solving systems of linear equations in two variables. This is part 2. In part 1, we talked about what a system of equation in two variables is. We talked about the solutions and how to describe a system. We solved them by graphing and by substitution. So now in this lesson, we're going to solve systems of linear equations in two variables using elimination. And then at the end, we're also going to be given a system in an ordered pair and determine if it's a solution of the system or not. Okay, so solving a system by elimination. So what we do is we manipulate the equations by multiplication so that we can easily add or subtract the equations to eliminate a variable. And what this does is it leaves us with a linear equation in one variable that we know how to solve. We solve for that variable, and similar to what we did previously with substitution, once we have the value of one variable, we can plug it into one of our given equations to find the value of the other variable. So let's see what this looks like. Okay. So solve a system of linear equations using elimination. So we're given 6x plus 5y equals 11 and 9x plus 8y equals 20. So what we want to do is we want to get our x's or y's to the same number with opposite signs. So for instance, just for a second, let's say we had negative 10x and positive 10x. Okay, when we add these together, they would eliminate or they would cancel out. So that's what we're trying to do when we're solving a system using elimination. So it's your choice if you want to eliminate x or y. I recommend doing the one that's easier. Okay, so if we look at x, we have 9 and 6. So using multiplication, we can get 9 and 6 to 18, or 1 to positive 18 and 1 to negative 18, so that when you add, they cancel out. If you look at 5 and 8, the smallest number that those can both get to is 40. So you choose which way you want to go. I'll probably work with the x's because I'll be multiplying by smaller numbers. Okay, so I'm going to get the 6x to 18x by multiplying by 3. And if I multiply that by 3, I have to multiply everything by 3. Okay, that preserves the equality, the equal sign, or that the left-hand side is equal to the right-hand side by doing the same thing to every term. So this gives me 18x plus 15y equals 33. For the bottom equation, I want the 9x to be negative 18x, so that when I add the two equations, I eliminate x. So this is negative 2, negative 2, negative 2. Okay, so I have negative 18x minus 16y equal to negative 40. So now what I do is I add the two equations. So 18x minus 18x, these cancel to give me 0. 15y plus negative 16y is negative 1y. We still have an equal sign. We're just adding these up. We still have the left and the right. 33 plus negative 40 is negative 7. So I'm left with negative y is equal to negative 7. Divide both sides by negative 1. Y is equal to 7. Okay, so now that I found y is equal to 7, I plug in 7 into either equation that I was given, and then I can find x. It doesn't matter which one we use. I'll use the top one. So we have 6x plus 5 times 7. So instead of y, we have 7 is equal to 11. Okay, so we have 6x plus 35 equals 11. And we solve this like we would a linear equation. Subtract 35 from both sides. 6x equals negative 24. So x is negative 4. Okay, so on the next slide, we will put this all together. We'll describe the solution and we'll describe the lines. So here there's one solution. Remember, it's written as an xy pair. So this would be written as negative 4, 7. The system is consistent because there's at least one solution, and the lines are independent because they are different lines. Moving on to the next example, solve the system of equations. So here I just put solve the system because I wanted to talk about when substitution is appropriate and when elimination is appropriate. Substitution is useful when you can easily solve one of the equations for y, probably without working with a lot of fractions, or a variable's alone on a side by itself. Otherwise, when it looks like this, you'll more than likely use elimination. Okay, so I'm probably going to work with the 3 and the 2. Because I can get 3 to positive 6 and 2 to negative 6, or vice versa. You just want one of them to be positive, one of them to be negative, so that when you add, they cancel out. So I'm going to multiply this equation by 2 and the bottom equation by negative 3. So this gives me 6x minus 24y equals 12. And I'm multiplying the bottom by negative 3. So we have negative 6x plus 24y equal to negative 12. Okay, so when I add these up, 6x plus negative 6x cancels. Negative 24y plus 24y cancels. Equals 12 plus negative 12 is 0. So we get 0 equals 0, which is a true statement, right? So we talked about this previously with solving equations. This means that there's infinitely many solutions, okay, or that the lines are identical. So let's talk about how to write our answer. So in the computer software, you'll see infinitely many, and you'll see x, and then you'll see a blank. Remember that when a system has one solution, we write an x-y pair. Well, in this case, y is not a number, it's the equation of the line, because that line is what solves the system. So in order to fill in this blank, what we do is we take one of the equations. I'm going to take 3x minus 12y equals 6. And we solve it for y, because that's in the y position of our coordinate. Okay, so subtract 3x. And we have negative 12y is equal to negative 3x plus 6. And then we're going to divide everything by negative 12. I don't know why I wrote 16. This should be 6. Okay, so this gives us y is equal to negative 1/4 x minus 1/2 if you reduce. So this is our y. This is what y is equal to. Goes in here. So you would write negative 1/4 x, or this is positive 1/4 because we did a negative divided by a negative. So negative divided by a negative is positive 1/4 x. So let me fix that. And then that's minus 1/2. Okay. So this system then is consistent because there's at least one solution. But since it's the same line, it's described as dependent. Okay. Next, solve the system of equations. So 6x minus 4y equals 2, 3x minus 2y equals 5. Since they're stacked together like this, I'm going to use elimination. This time I'll work with y values just so that we work with something different, and you can see that it's up to you which one you choose to eliminate. So in my top equation, I have 6x minus 4y equals 2. Then I have 3x minus 2y equals 5. I'm going to match 2y to be positive 4y so that when I add them, they cancel out. So if I need to multiply this by negative 2, I multiply everything by negative 2. So I have 6x minus 4y equals 2. And then in the bottom, I will have negative 6x plus 4y equal to negative 10. So if I add these up, negative 6x and positive 6x cancel. Negative 4y and 4y cancel. So I get 0 is equal to negative 8, which is not true. So this would be a case of no solution. So if we talk about our solution, it's no solution. The system is inconsistent because there is no solution, but it is still independent. The lines are independent because they're different lines. They're not the same line. Okay, the only time we have the same line is when we have infinitely many solutions. Okay. So determining if an ordered pair is a solution. So in order for an ordered pair, x comma y to be a solution of the system, it must satisfy all equations in the system. So when you plug in x and y into the equation, it should be true into all of the equations in the system. And then if you're given the value of one of the variables, x or y, you can find the value of the other for the system of linear equations in two variables. So let's see what this looks like. So first, example 1, determine whether the given ordered pair is a solution of the system of equations. Use alphabetically ordered variables. So I wanted to talk about this. So we have equations using a and b. So alphabetically ordered means this would be a comma b. Okay, so what we do to check if it's a solution is we plug a and b in both equations and see if it makes the equation true. So in the first one, a is 9, we have minus, and then the b value is negative 3, and we want to know if this equals 12. 9 minus negative 3 is 12, so we have 12 equals 12. It satisfies the top equation. Let's look at the bottom. So we'd have 2 times a. A is 9. We want to know if that's equal to negative 3 plus 15. This is 18 is equal to 12. No. So since it only satisfies the top equation, this is not a solution because it did not satisfy all equations in the system. Okay, we'll use the same equations that we did on the previous slide, so you don't necessarily have to rewrite those in your notes, but we have a different ordered pair, 3, -9. So this is a comma b. So let's check the first equation. So we have 3 minus -9. And the reason it's minus and negative is we have a minus b. So we have to do a minus b. b is -9. Okay? And we want to know if this equals 12. 3 minus -9, we get 12 equals 12. So this one checks out. And let's check the bottom one. So 2 times 6 equals, and then we have, or 2 times 3. I think I evaluated that already in my brain. That happens sometimes. -9 plus 15. So this is 6 is equal to 6. So it checks out. So yes, 3 -9 would be a solution to the system, or is a solution to the system, because it satisfies all equations. Next, you'll see something like this. For the system, the value of one variable is given. Find the value of the other variables. So we have 4a plus 5b, 3a minus b equals 16, and we have a equals 6. So this is an equation, but it's telling us the value of a. So all we have to do is substitute this in to the first or second equation to find the value of b so that we find the solution. I'm going to substitute it into the second equation because those numbers are smaller. Okay, so we have 3 times a minus b equals 16. Okay. So here we have 18 minus b is equal to 16. We subtract 18 from both sides. Negative b is equal to -2. And if you want, divide by -1 to see that b equals 2. Okay, so that would be the value of the other variable, and then writing this as an alphabetically ordered pair would be a comma b, so 6, 2. Thank you for watching. If you have any questions, please feel free to reach out to me.